Welcome to your video on bond polarity. So, when we're talking about bond polarity, we're talking about a very specific bond, and more often than not we're talking about covalent compounds. What this is eventually going to lead to is a discussion of the polarity of molecules, and molecules are really a product of covalent bonding. So the question is, with bond polarities, will a particular bond produce a separation of charge? In other words, is it going to produce positive and negative poles? Figuring out bond polarity is pretty simple. So let me show you maybe two examples. So here, the example is going to be oxygen bonded to fluorine. So this scale down here, we'll get to in just a second. In order to figure out if a bond is polar, the first thing we're going to look up is the electronegativity values. Electronegativity value for fluorine is 4.0 and for oxygen is 3.5. In order to figure out if the bond, and we're talking about this bond right here, is going to be polar, we have to look at the electronegativity difference. So if we looked at the difference between the electronegativities, that puts it at 0.5. Here's where the chart comes in. What you're going to do is cross-reference the chart and see where the electronegativity lands. For this one, it would land in this range, between 0.4 and 1.0, which is moderately polar covalent. So this would, in fact, be a polar bond. Since it's a polar bond, we want to map on the partial charges. So the fluorine side, since it has a higher electronegativity, is partial negative. The oxygen side, since it has a lower electronegativity, is partial positive. There we go. So there's a separation of charge, and this would be considered, again, moderately polar covalent. And again, what this means is that there's going to be more electrons around the fluorine more of the time. That's where you're getting the partial charge from. It's not permanent, it's partial. Let me show you another example. For this next example, we're going to go with hydrogen bonded to oxygen. Doing the same thing. Let's look at the electronegativity values. Oxygen is a 3.5. Hydrogen is a 2.1. So that's going to give us an effective electronegativity difference of a 1.4, which is going to put it in this range right here. And that 1.4 means that this guy is very polar covalent. So very polar covalent, VPC. And since it's very polar covalent, it makes it appropriate for us to map on the partial charges. Oxygen has a higher electronegativity than hydrogen, therefore the charges map on that way. There's going to be more electrons around the oxygen more of the time. That gives it the partial negative. Hydrogen is going to be a little deficient. That's its partial positive. Cool. One more example, and then that'll be it. So here, this last example, I want to prove a point that refers back to something we learned in the bonding unit, which is that when you have a metal and a non-metal, that gives you an ionic compound. Here's another look at that. So what I did here is I took table salt, NaCl, and I put their electronegativity, sodium with a 0.9, chlorine with a 3. We know that metals, like sodium, have a low electronegativity. Chlorine, a non-metal, has a high electronegativity, and that's kind of what results in ionic bonding. If we look at the electronegativity difference here, it comes out to 2.1, and that puts us above 2, and that's in the ionic range. It all sort of fits together like a puzzle. Chlorine, since it's more electronegative, is going to have more electrons around it more of the time than sodium. It's sharing, but it's so skewed that we really don't call it sharing anymore. We call it electron exchange. So sodium actually gives up its electron to chlorine. That results in positive sodium and negative chlorine. And the charge characteristic is permanent. And that's a big difference between ionic and covalent compounds, is that in ionic compounds we have ions, and they take on a permanent charge character. Whereas in covalent compounds, in our polar bonds and such, we see something that's more impermanent. The charge is partial, which means it's not permanently charged. So, anyways, just showed you three examples of bond polarity and trying to figure it out. Very simple process. Look up the electronegativities, subtract them, and compare the answer to the chart. That's all. Take it easy.